I'm going to show you a trick that allows you to take one voltage and subtract a second voltage from it. So the output will be the difference of these two voltages. So it's useful if you have an array of batteries in series and you want to know each cell's actual voltage rather than just the total voltage of your batteries. It's also useful to take two wires, maybe a signal and a ground, and if you run them next to each other and they pick up noise along the way and it affects both of them, the circuit I'm about to show you takes that noise out. So you're only left with the signal that you originally transmitted. So for example, if your signal that you want to transmit is a square wave, maybe it goes from 3 volts to 5 volts, and then it comes across some noise in the transmission line. And if you have a ground signal running next to that and it also runs into the same noise, at the output here, if you take the difference of the two voltages, you can see that it's 3 volts here, 5 volts here. But when you get to this point, they both shift. So maybe if the noise came along and it raised both by 1 volt, this is 6 and now this is 1. The difference of those two is 6 minus 1 takes it back to 5 volts. You get your original signal back with no noise. So how do you do it? This is a difference amplifier and it'll take the difference of the two input voltages. So let's analyze the circuit and figure out what V out is to see what's going on. Current going into the two terminals is 0 amps and the voltages at the two input terminals is the same. Whatever voltage sits at this non-inverting input, the inverting input will also have that same voltage. Let's do a KCL analysis around this inverting input. Since no current flows into the inverting input, we've only got two paths where current can flow. KCL tells us that the sum of current out of a node is equal to 0 amps. So the current across this resistor is the voltage at the inverting input minus V1 divided by R1, and current I2 is equal to the voltage here minus voltage out divided by R2, and that's equal to 0. Now let's do a KCL analysis at the non-inverting input. So again, there's two paths current can flow because none of it goes into the op amp. There's I1 across the resistor R1 and there's I2 across the resistor R2. So an I1 is equal to the voltage here minus the voltage there divided by R1. Current I2 is the non-inverting input voltage minus ground over R2. So now we've got two equations. I'm going to rearrange this equation to solve for V plus, which is the voltage at the non-inverting input, and that gives us that voltage is equal to this. Now I'm going to rearrange our first equation and figure out what V out is. We get this. So now we have an equation in terms of our input, the resistors, but V minus is still sitting here. We know that V plus is equal to V minus because of the ideal op amp rules. So if I substitute V minus into the equation, so here we go, I've just plugged V minus, cancels straight out. That gives us a much cleaner equation. Now we're left with just this. We can also see that 1 over R1 can be taken outside, so we can see the output. And if you just make these resistors the same, for example, if you make them all 1000 ohms, 1000 over 1000 just cancels out and you're left with only V2 minus V1.